Hello, the purpose of this video is to go over section 7 of chapter 2, graphing techniques. In this section we will stretch, we will translate, we will talk about odd functions and even functions, and we might even do a little reflecting. But first we're going to start off with stretching. So here I have a function. I'm going to call it f, and f actually happens to be defined as the absolute value of x between -4 and 4 and is not defined elsewhere. So it has a domain of from -4 to 4 and a range from 0 to 4. And we want to talk about what might happen if I actually take that function f and I multiply it by some non-negative real number a. Well, actually I didn't want to do that. I wanted to have g of x is equal to some non-negative real number a times f of x. Well, if you do that, at least for the case when a is equal to 1, you are going to get this. Basically, if a is equal to 1, g of x is simply equal to f of x, which makes perfect sense. But if we increase a, we will find, so it's greater than 1, we will find that the range is increasing and the graph is actually being stretched upward. And we would call that vertical stretching. So when a is greater than 1, the graph of y is equal to a times f of x is a vertical stretching of f. I probably should have given myself more room in the guided notes. And as you then might suspect, if a is less than 1 and greater than 0, then our graph is shrinking. The graph basically gets smaller and smaller until it gets to a flat line between -4 and 4. So we would call that a vertical shrinking. One thing that you can notice, however, is that the domain always stays the same. When we multiply f by some non-negative real number a, the domain will always be between -4 and 4 for this function. But however, the range does change, and indeed as x goes all the way up to infinity, we pretty much just have a vertical line. Of course, I can't get it that far. I only have it set so that a can get all the way up to 5. Okay, cool. All right, well, what about instead of multiplying f by a, suppose we multiply the argument by a. So we would have some other functions just called h of x is equal to f times f of a times x. So we're going to take our independent variable a. No, we're going to take our independent variable x. We're going to multiply it by a, and we're going to take that product and put that into f. And if you do that, what you're going to have is a function that looks like this. Well, when a is equal to 1, hey, we're just back to f of x. But look what happens when a is greater than 1. There we go. Then, as you can see, the domain actually gets smaller and smaller. As a matter of fact, when a is equal to 2, right there, well, then the domain ranges only from -2 to 2. And why is that? Well, when x is equal to -2, a times x is equal to -4, and f of 4 is equal to 4, which is why we have a 4 here. But what you can see is that we are shrinking. We are shrinking, and we are shrinking horizontally. It's getting small. The domain is getting smaller and smaller. So when a is greater than 1, we have a horizontal shrinking. However, notice the range never changes. The value of the value of h in this particular case never gets above 4, unlike the value of g, which will get higher and higher and higher, even though they have the exact same shape. H stops here. The g just keeps on going. And clearly, and as you can see, when a is less than 1, then the graph gets wider and wider. However, it still never exceeds, however, the range never changes until you get to that isolated case when a is equal to 0. So here we have a horizontal stretching. Okay, and that brings us to our first set of examples. And we can actually, I'm not going to plot them here because my handwriting stinks, but I will show you what they are on GeoGebra. So let's start off with f of x. Well, there it is. Okay, well, what about if you multiply it by 2? Well, I can show you what that looks like by, well, I need to get my slider back up. By taking my slider all the way up to 2. There is 2 right there. And that's what it will look like. It will be basically a v that starts at -4, 8, goes down to the origin, and then back up to 4, 8, which is what we have right here. And then finally, the next for c, if you wanted to look at that one, we would just take our slider, move it down to 1/2. There it is. And here, once again, it's a flatter v. In this case, it starts at -4, 2, goes down to the origin, and then back up to 4, 2. And then for the last one, I cannot show you that one with this one because here we are multiplying the argument by 2. So this would be this function here, my version of h, and we can show that by bringing a back up to 2. I wanted to get rid of the other one. There. And here we have a tighter v. We start off at -2, 4 for part D, down to the origin, and then back up to 2, 4. So that is pretty much all we have for stretching and shrinking. Once again, for vertical stretching, if we multiply the function by a, we have vertical stretching when a is greater than 1, vertical shrinking when a is less than 1. If the argument is being multiplied by a, then we have vertical shrinking or vertical stretching when a is less than 1 and vertical shrinking when a is greater than 1. And our next topic is going to be reflections. Okay, so here I have a function. This function is called f. This actually happens to be, in this case, f happens to be equal to the square root of x when x is between 0 and 5 and not defined anywhere else. Now, suppose that I actually wanted to take this function and reflect it across the x-axis. Well, what do I need to do? Well, I need to take every point here and multiply it by -1. If I do, I will have a new function, which we call negative f of x. And there it is. So as it turns out, that the graph of, if you take f of x and multiply every point and multiply that function by 1, you are going to get a reflection across the x-axis. Moreover, since this is a reflection, it turns out that that every point that lies on our base function, like this one right here, if this point lies on the base function, then the point x negative y, negative, where's my negative? There's my negative. Negative y, sorry about that, will lie on its reflection. So if point xy lies on the graph, then the point x negative y lies on the reflection on its reflection about the x-axis. All right, well, if we can reflect about the x-axis, we can also reflect about the y-axis. So we reflected about the x-axis by multiplying, by basically taking the negative of the function. So instead of this basically is negative f of x. If we want to actually reflect along the x-axis, we just need to take the negative of not the function, but the argument of the function. And when you do, you will have this, which now you can possibly see. And, well, that should be, where is that? There it is. And this is reflected about the y-axis. Okay, well, once again, that basically means that if that the graph of f negative x is going to be reflected across the y-axis. Okay, better yet, if xy is on the graph of the of our base function y equals f of x, then negative xy will actually be on its reflection. And I can show you that here. So let's take our point xy. All right. Well, notice that x negative y lies on the reflection about the x-axis. And then negative x, where is that? Negative x comma y, which is right there. Negative x y lies on the reflection about the y-axis. So suppose you have a function f of x, and you want to know what the reflection is about the x-axis. Well, then that will just simply be negative f of x. Suppose if you have a function f of x and you want to reflect it about the y-axis, then that will be f of negative x. So this is an x-axis reflection, and this is a y-axis reflection. And this brings us to our examples, and you sort of see them here. The first one is to graph each function. And we're kind of assuming that we already know what the graph of f of x is, or what the square root of x is. That's pretty much this. So then the graph of that function would simply be nothing more than a reflection of this particular function, the square root of x about the y-axis, which of course would give you this. However, now it would extend all the way to infinity. So that basically is part A. And then for part B, that is basically a reflection about the y-axis, so it will look like that. And the comments that we made also apply here. If xy is on the graph of y equals f of x, the graph of negative xy will be on the graph of its y-axis reflection. And that is pretty much all that we have to say about reflection. And that brings us to symmetry. So let me bring that one up. And here is a graph that is symmetric about the y-axis. And you can see that it is symmetric because basically the y-axis cuts these into mirror images of each other. This section right here is a mirror image of this partition of the graph right here. Okay? The other thing that you can notice is that for any point on this graph, we can call this xy, x comma y, then negative x comma y is also on this graph, and that actually is the mathematical definition of symmetry. And what does that kind of imply? Well, it implies this. If you replace x with negative x into your equation, and you come up with the exact same equation, or one that has the exact same solution set, then we can say that the graph of that relation is symmetric, which comes in handy for the case if you do not actually happen to have a picture of the graph. Here you can pretty much look at it, but if you don't, what you can do is you can substitute negative x with x, and if you get the same equation, then you are good to go. As far as our notes are concerned, and those plots are now going to disappear, for a graph to be symmetric about the y-axis, then the point negative x comma y must be on the graph whenever xy is on the graph. Okay? So let's take a look at another function, and here it is. This one is 10 to the 5th minus, no, I'm sorry, y to the 5th minus, no, y to the 10th minus 5 is equal to x. And as you can see, this graph is not symmetric about the y-axis, but it is symmetric about the x-axis. One thing that you can also tell is that this is not a function. Why? Because it fails the vertical line test for every value of x greater than or equal to negative 5. However, what you can see, let me bring that back down, is if xy is on the graph, then x negative y, that should be negative y, not y minus, is also on the graph. And furthermore, if you actually have an algebraic expression for this graph, and if you replace y with negative y, and if it results in an equivalent equation, then you can say that this graph is symmetric about x, which is my last point right there. All right, now as you can see, this graph is not a function. It turns out that every graph that is symmetric about x is not a function, with one and only one exception, or with a collection of exceptions. And those are graphs where g of x is equal to 0. This is the only one that is symmetric about x and also happens to be a function. To finish up our guided notes here, for a graph to be symmetric with respect to the x-axis, the point x negative y must be on the graph whenever xy is on the graph. All right? And now for a graph of an equation, so if suppose you have an equation but not a graph of it, is symmetric to the x-axis, I'm sorry, to the y-axis, if the replacement of an x with negative x results in an equivalent equation. And furthermore, a graph of an equation is symmetric with the x-axis if the replacement of y with negative y results in an equivalent equation. And here we have some examples. So here we want to test to see if these functions or if these equations are symmetric with either the x-axis or the y-axis. Okay, so what we're going to do, at least for x-axis, we are going to change y to negative y and negative y, not 5, and see what happens. If we do, we will have negative y is equal to x squared plus 4. Solving for y, we would have y is equal to negative x squared minus 4. This right here, these are not equivalent equations, so we would say that this is not symmetric. Okay, for the y-axis, okay, for that case, we are going to replace x with negative x and see what happens. In this case, we will have y is equal to negative x, the entire thing squared, plus 4. Evaluating this, we are back to y is equal to x squared plus 4. And so these two equations, this equation and this equation, which now you can barely see, are the same. So we have that. So we have symmetry about y. Okay, so that takes care of the first one. Here we have not symmetric. Sorry if you guys can't read my writing. And here we have symmetry about the y-axis. Okay, what about this problem right here? To check for symmetry about the x-axis, we will let y be equal to negative y, or replace y with negative y, and that will give us x squared plus the quantity negative y squared is equal to 25. Evaluating that, we will have x squared plus y squared is equal to 25. So we have the exact same equation. As a consequence, and that is a y squared, not a y2. As a consequence, this is symmetric about x. What about the y-axis? So symmetric about x. Okay, well, what we're going to do here is we are going to replace y with x with negative x. Sorry about that near Freudian slip. And do the exact same thing. We will have negative x, the entire quantity squared, plus y squared is equal to 25. All right, and then evaluating this, we have x squared plus y squared is equal to 25. So we have symmetry about y, or it's symmetric about y. Okay, now what about the last one? Okay, once again, checking out the x-axis, we are going to replace y with negative y. And that will give me 2x plus negative y is equal to 4. And if evaluating that, I will have 2x minus y is equal to 4. And as you can see, these, that should be a 4, my apologies, this equation is different than that equation. They are not the same. As a consequence, we are not symmetric about x. For the y-axis, we're going to replace x with negative x. And that will give me 2 times negative x plus y is equal to 4. And evaluating that, I will have negative 2x plus y is equal to 4. And this is not the same as this equation up here either. So this is also not symmetric about y. So if you have an algebraic expression and you cannot take a pic and you cannot get a graph of it like what we can do over here in GeoGebra, what you can do, one, is just conduct this test. These two tests right here, one for the x, one for the y-axis, and that will assess its symmetry. So we have symmetry about the x-axis. We have symmetry about the y-axis. We can also have symmetry about the origin. And here is a rather non-descriptive graph that shows you that. But it does give you the criteria. It turns out that the graph is symmetric with respect to the origin if we replace both x with negative x and y with negative y, and it results in what we would call an equivalent, or in this case possibly the same equation. So I'm going to write in here equivalent, and let's take a look at a couple of picture examples. Okay, so here is f of x is equal to the to x to the 5th power, and notice that it happens to be an odd power, and this actually is true for any x being raised to any particular odd power. So notice that this particular point, we're going to call this point xy, lies on the graph. Then for it to be symmetric about the origin, the point negative x, negative y also lies on the graph. And that is the primary criteria for symmetry about the origin. For example, this circle, which is centered at the origin with radius, or any circle which is centered at the origin, will also be symmetric about the origin. Similarly, any linear function with a slope of 1 or -1 that crosses the origin is also symmetric about the origin. However, the criteria for determining symmetry about the origin algebraically is this. If you can replace x with -x and y with -y, and you come up with the exact same equation, then you have symmetry about the origin. And that brings us to our next couple of examples. Okay, so here we want to test for symmetry about the origin, and we're going to look at this one, which is x squared plus y squared, which is a circle centered, no, I'm sorry, this one is x squared plus y squared equals 9, which is a circle which is centered at the origin that has a radius of 3. So we know for a fact, since it's centered at the origin and it's a circle, we're going to have symmetry about the origin. But let's just go ahead and algebraically prove that. So to test that, we are going to replace x with -x. We are going to replace y with -y. And we are going to see what happens. Here we're going to have -x squared plus negative y squared is equal to 9. Well, -x squared is just x squared. -y squared is just y squared. And that's going to be equal to 9. So we have symmetry about the origin. Okay, now for the next one we have y is equal to x squared. You can look at that and you know for a fact that and you can tell that we have symmetry about the y-axis. But we will not have symmetry about the x-axis. So chances are this will not be symmetric about the origin, but let's just go check and find out. So we're going to replace x with -x. We're going to replace y with -y. And then what gives us -y is equal to -x, that quantity squared. Evaluating that, we will have -y is equal to x squared, or y is equal to -x squared. These are not equivalent relations. These are not equivalent equations, so this is not symmetric about the origin. And so we can summarize our symmetry tests here. And basically you just need to think about opposite variables. For symmetry about the x-axis, the equation will be unchanged if y is replaced with -y. Okay? For symmetry about the y-axis, the equation is unchanged when x is replaced with -x. And for symmetry about the origin, the equation, you have that if you replace, well, x with -x, y with -y, and the equation is unchanged. This pretty much is what you need to remember relative to symmetry about the x-axis, y-axis, and the origin. And that brings us to even and odd functions. Okay, and here we have an even function. One thing that you can tell about the even function is that it is symmetric about the y-axis. As a consequence, a linear function is called even if f of x is equal to f of minus x for every single x in the domain of x. If that's as a consequence, we can say that the graph is symmetric to the y-axis. And as you can see, this graph basically meets that criteria. There's also one other cool thing about this graph. Notice that here is a graph of a polynomial. This conveniently happens to be part A in example 5. And notice that this polynomial has only even exponents. That this one here actually has an x to the 0 across it. So if a function that is a polynomial in x has only even exponents, where x to 0 has the even exponent 0, then that function will always be even. Okay, so as a consequence, for part A, we have an even exponent here, an even exponent there, we have an x to the 0 there, which is also even. This, just by looking at this, we can tell right away that this is an even function. The other way that we could determine this is by checking for symmetry about y. So if we replaced x with -x, we would find that f of -x is equal to f of x, and we could actually show that algebraically. But it's just enough to identify these three exponents as even. Therefore, it is an even function. Okay, so let's take a look at an odd function. And here is an odd function. this function happens to be symmetric about the origin. As a consequence, it has this property. If you take the function f and evaluate it at negative x, you're going to get the exact opposite. And that is consistent with the property of symmetry about the origin, where if xy is on the graph, well then negative xy or negative x, negative y is also on the graph. So this is symmetry about, so an odd function is symmetric about the origin. Furthermore, we can say the function is odd if f of x is equal to negative f of minus x. We have an example of that here. Here is our point xy, and then this point, which would be negative x, negative y, is also on the graph. Also notice that the this function is actually, well, it's right down here. It is g of x is equal to 6x cubed minus 9x, which is part B for our example. And notice here that we have strictly a polynomial with strictly odd exponents, and that is an indication of what we have seen before. And that is, if you have a polynomial with only odd exponents on x, then the function from that polynomial will be an odd function. So take a look at our example for part B. Here we have 3, which is an odd exponent. Here we have an implied 1, which is also an odd exponent. So this here is going to be an odd function. Okay, now let's take a look at part C. Here's part C. Here's part C in our example. And here we have f of x is equal to 3x squared. So we have an exponent. We have an even exponent plus phi of x, where we have an odd exponent. So since this has a combination of both even and odd exponents, this will neither be even or odd. Remember, for a polynomial to be even, it must only have even exponents. For a polynomial to be odd, it must only have odd exponents. This has a combination of both, so it is neither even or odd. And if you don't believe me, this is a graph of that particular function. And notice that this function is neither even nor odd. There is no symmetry about the y-axis, and there is no symmetry about the origin. And that brings us to translations. And no, I do not mean translations as far as the language is concerned. I mean translations of graphs. So let's start off with our basic graph, our basic function right here. Let me see if I can get that a little bigger. This is f of x is equal to the absolute value of x between negative 4 and 4. So it basically is, it is a v that goes, it is a v whose domain is from negative 4 to 4 and its range is from 0 to 4. And the question here is, well, what happens if we actually create a new function, g of x, which is equal to f of x plus some number c, where c is a real number? All right, well, let's take a look. Okay, well, and this is f of x plus c, what we have here. Well, notice that if I increase c, the graph shifts up. Okay. And so for every point xy that's on f, the corresponding point on g is going to be x, y plus c, because we are shifting up or down. Just to show that, here, well, here's the point. This is the point 0, 0. And this point is the point, this point is the point 0, comma 0 plus 2. Let me close that. So that's pretty much what we're dealing with. What else can we say about this? Well, it turns out that if c is positive, then the graph shifts up by whatever the amount c happens to be. So the graph is translated up c units if c is positive, and if c is negative, then the graph is translated down by whatever the absolute value c happens to be. So we would call, the graph G is nothing more than a vertical shift of the graph of f, which is what I was supposed to say here, but I sort of forgot. All right, so now let's take a look at what happens if we actually change the argument of f by c. So now we're going to have our new function. It's going to be h of x, and it's going to be equal to f, which is going to be a function of the argument x plus that real number c. What is that going to look like? Well, in this particular case, it's going to look like this. So in the case when c is equal to 0, it is not really all that impressive. However, let's suppose I move this by 1. Okay, no, how about I move it by 2 instead? Well, notice then for every point xy on the graph, then we have the point x minus c comma y on the shifted graph. To illustrate that, here, once again, here is our point 0, 0 on the origin. Well, this is 0, comma 0 minus 2. No, I actually did that. That is 0 minus 2, 0 minus 2, minus 2, 0 on the shifted one. So it turns out here that the graph will be the same as f, but it will be translated to the left if c is positive. And then when c is negative, it gets translated to the right. And the graph to c is what we can call a horizontal shift. Okay, so let's work some examples. And here is example 6, where we are going to translate a graph vertically. So we're going to start off with our regular function, which is just f of x. There it is. And the question here is, what is f of x minus 4? Well, first I need to do that. Well, to look at that, we need to look at that. Let's take a look at g of x. Here it is. And what we're going to do is move c down to negative 4. I don't want to look at h just yet. And there, well, if I can get it there. There it is, and there it is. Notice that base is nothing more than the shift of f of x down 4. And it's so basically it's nothing more. It's a vertical shift of f of x down 4 units. Okay, so that's what that would look like. What about for the case where we have f of x minus 4? In that particular case, we will have that. Okay, remember a shift of a shift of a negative value is basically a shift in the right direction for 4 units. So that's nothing more than our original graph shifted to the right 4, and it will look just like that. And that brings us to this particular line. If to summarize our translations, if we actually have y is equal to f of x, we add c to it, and that's going to be an upward shift by c units. So this is going to be an upward shift. F of x minus c will be a downward shift. What if you add positive c to it? Well, that will be, once again, a shift to the left. That actually looks kind of cool. So shift to the left. So it'll be a left shift. And similarly, shift by negative c, or by negative c will be a shift to the right. And that brings us to, yes, you guessed it, our very last example. Woohoo! And here is example 8. Okay, and here we're going to talk about how to handle more than one transformation of a certain function. So here we have f of x is equal to negative the quantity, the absolute value of x plus 3, and all that's going to be plus 1. So we actually have 3 transformations here. We have a horizontal shift to the left, we have a vertical shift up, and we have a reflection about the x-axis. Now typically it's best to do the multiplicative transformations or the reflections first. So let's go ahead and do that. Here we have basically the absolute value of x. So to do the first part again is going to be reflecting, is to do the negative sign reflecting about the x-axis. That will give me this, which is basically negative the absolute value of x. Once we've done that, then we can go ahead and we can shift it to the left by 3. And in this particular case, the order doesn't matter. And if I do, I have that. I have that. And then if I shift it up by 1, I have that, and that would be the plot of that particular graph. Okay, let's take a look at 8b. Okay, so here we have h of x is equal to 2x plus 4. The first thing we can notice here is that we can actually factor out a 2, so let's go ahead and do that. Okay, and then this is going to be equal to h of x is equal to the absolute value of 2 times the absolute value of x minus 2. And that is equal to, and since the absolute value of 2 is 2, this is what we have. So now what we see here is a vertical stretching of 2 and then a vertical shift to the right. And once again, it might be better to apply to the multiplicative transformation to stretching before we do the shifting. So let's go ahead and do that. First, we start off with our basic function, which is the absolute value of x. We are going to multiply that function by 2, which will give us a vertical stretch. There it is. Okay? And then, now, I want to shift it to the right by 2, and there you go. That actually is the final answer. And that brings us to our final example, example 9. So here we have a graph, and we want to basically do a couple of transformations on this graph. Now, what I did here was I graphed the function. I also graphed basically some important points. I graphed the endpoints. I graphed the minimum. I put out the point where it crosses the origin, and I also put out the point where it's maximum. And what I'm going to do in doing these transformations is I'm going to transform each point, and then I'm going to draw the graph. So here is our basic graph, and our first problem is to basically shift this upward by 3. F of x plus 3 is basically an upward shift. So here I have shifted every single point up by 3. This is up by 3, and so forth. And now I'm going to connect the dots, and that is what the new graph will look like. So that's part A. Now part B is a shift to the left by 3. So to do that, I'm going to take each of these points and I'm going to shift them to the left by 3. There they are. 1, 2, 3, 4, and as you can see, they're all shifted to the left. And then finally, I'm going to connect the dots. And there you go. Okay? Thirdly, for the third problem, we are going to shift the points to the left by 2, to the right by 2, and then up by 3. Negative is a right shift. So what's that going to look like? Well, once again, I'm going to move each of the points to the right by 2, 1, 2, and then up by 3, 1, 2, 3, which I've done for every single one of these points. And then when I connect the dots, the graph will look like the green line there. And then finally, D is reflection about the x-axis. So remember, for that one, if xy is on the graph, so these points are on the graph, then x negative y will be on the other graph. So here, since y is 0, nothing changes. Here we have x negative y down here, and we have x negative y up there. And if I connect those dots, that is what the graph looks like. That would be a vertical, or that would be a reflection about the x-axis. And that is it for this particular section. If you have any questions, please feel free to contact me. And this is Bob Boyle signing off.